Open your repository's CLAUDE.md file. Now check the version from 6 months ago. It's longer. They always get longer. The median instruction file currently holds 39 instructions, with the 90th percentile reaching 131. You cannot simply delete these files. Repositories equipped with agentic instructions consistently finish tasks faster and use fewer tokens. But you cannot let them grow indefinitely either. As arbitrary constraints accumulate, an LLM's instruction-following capability degrades sharply. Engineers are stuck managing a degrading asset. Applying standard code maintenance intuition to LLM prompts fails completely. We can observe exactly how this fails across 1,867 public GitHub repositories and over 247,000 instruction lifetimes. Over a prompt's lifetime, its size swells by 226%. Every single commit adds a net average of 4.9 instructions. Developers eventually cope by bulldozing the file. They perform a wholesale rewrite that arbitrarily cuts the instruction count in half. Almost immediately after this rewrite, the file regrows. Look at the rate of that regrowth. Before the rewrite, the file grew at 4.1% per commit. After the rewrite, it grows at 4.9%. 76.8% of all instruction deletions occur during these mass bulldozes, rather than as targeted removals of specific rules. Deleting half the file resets its absolute size, but ignores the root cause. This sawtooth pattern is driven by a mathematical phenomenon called catastrophic remembering. Maintaining a prompt requires estimating an unobservable set of constraints based on censored, noisy feedback. To safely delete a single instruction, a developer must prove its removal contributes zero negative impact across all of those hidden constraints. Systemic redundancy makes testing one by one impossible. 2 instructions covering one constraint look perfectly safe when removed individually. The error only triggers if you delete both. Guaranteeing safety requires checking every possible combination, an O of 2 to the power of D counterfactual check. It is mathematically incomputable. This introduces the concept of latent reasoning, the unrecorded why behind an instruction's creation. Writing down that reasoning when an instruction is created costs O of 1. Deducing it after the fact costs O of 2 to the power of D. The probability of a developer recovering that reasoning starts at 1 and decays towards 0 as the file ages. Once latent reasoning decays, a rational maintainer keeps every instruction to avoid breaking unknown constraints. Deletions stop, additions continue, and the prompt's equilibrium size diverges toward infinity. The standard assumption in engineering is that prompts bloat because instructions go stale, and people simply forget to delete them. If staleness were the cause, the probability of an instruction being deleted, its deletion hazard, would rise as the instruction ages. We can test this against the empirical data of 28,426 tracked instruction deletions across GitHub. This chart graphs instruction age against deletion probability. The data reveals a log hazard slope of negative 0.032 per commit. Deletion hazard falls over time. The staleness theory is incorrect. A secondary argument suggests that these fragile instructions simply break and die early, skewing the overall curve downward. But the data shows the deletion hazard drops significantly faster based on the number of human authors editing the file. New authors lack the original latent reasoning for existing instructions. Without knowing why a line exists, they refuse to delete it. The empirical data matches the exact mathematical signature of imperfect recall. To fix this bloat, we need to test a solution. But in the real world, we cannot measure excess size because the optimal instruction set, the minimum cover, is completely unobservable. This measurement crisis is solved by a methodology called the inverted I-eval. Instead of giving an AI the instructions for a benchmark, those original known instructions are hidden by a firewall. They become our baseline optimum. The benchmark's code verifiers are kept active as hidden constraints, outputting only vague pass or fail signals. A fresh maintainer is then forced to reconstruct the prompt from a brief objective, operating entirely under these noisy, censored conditions. By knowing the optimum instruction set, but hiding it from the maintainer, this inverted setup creates a controlled environment where excess prompt bloat can finally be measured. The solution requires applying a 40-year-old software engineering practice to agentic prompts, the structural comment. For this comment to work, it requires a precise schema, a round counter, a lineage of falsified approaches, and a verbatim restore quote. A critical rule governs this architecture. The agentic harness must completely strip the comment before the prompt ever reaches the LLM executor. The standard instructions tell the executor what to do. The prompt comments exist solely to tell the next human or agent maintainer why. In the inverted IFEVAL environment, the control group maintaining a prompt for 15 rounds generates an excess prompt size of 60.4%. By equipping the maintainer with informative comments, that excess size drops into the negative, stopping at -5.8%. Documenting latent reasoning at write time collapses an exponential maintenance problem back to 0.1. It removes 99.3% of long-term bloat without sacrificing accuracy. This intervention was then tested on wild IFEVAL, applying it to human-written prose constraints seeded with deliberate distractor noise. In these real-world conditions, extraneous distractors exact a severe penalty, costing 24.1 points of pure correctness. Prompt comments reversed this damage, lifting instruction following capability by a 23.1% relative margin over 3 rounds. These metrics have strict operational boundaries. The 23.1% lift is a recovery from seeded noise, not a baseline gain. The hazard slopes are observational lower bounds, and the data is restricted to English-only public repositories. Decades ago, software engineering solved the crisis of untrackable logic by strictly separating how code executes from why it was written. Letting latent reasoning decay in any complex logical system ensures that the system will eventually bloat completely beyond repair. If English is the new source code, we have to adopt a structured comment syntax for agentic instruction files. Otherwise, the ratchet will continue to break our systems.